I realise I'm giving quite a historical, sociological type of talk. That's okay, is it?
I think there is no better
Good.
way to finish a successful year than with doing still. But let me give just a brief snapshot overview of the many accomplishments that he's had in his fantastic career. Paul got his PhD in 1973 from the University of East Anglia. 1984, he joined what was then called the Imperial Council Research Fund, ICRF, and it's now called Council Research in the UK. Became a group leader there. Then 1989, he was a professor of microbiology at Oxford University. 1996, he became the Director General of the ICRF. In 2002, the Chief Executive of Council Research UK. 2003, he became president of Rockefeller University in the US. In 2010, director of what is now the Francis Crick Institute. So you can see right from that, not only did he have an outstanding career as a scientist, but also as a leader in science and also the thought leader in science, I believe. Paul is a geneticist and former president of the Royal Society. And he was awarded in 2001 the Nobel Prize in Physiology or Medicine, along with David Harper and Tim Hunt for discoveries of protein molecules that control the division and duplication of cells in the cell cycle. He has many other honors and awards. I don't even aim to list all of those. It is just too many. But just to mention among those, of course, he was knighted in 1999 and also in 2002 received the French Legion of Honor Award. He has over 60 honorary degrees and fellowships. And I will leave it at this. The topic of this exciting presentation today is going to be science as revolution.
Great. Well, can you hear me okay? Is it on? Good. So it's a pleasure to be here. I was last that I can remember at Rothamsted in the 1970s, would you believe? And the only building I can remember is that nice brick one at the front. Everything else looks a bit different. Because I was in fact trained as a botanist, as a plant scientist, with a minority course. Is there something not working?
Yeah, the microphone's not picking
I didn't think it was. Right. Which one do you want?
No, this one.
This one?
It's gone out of signal. I'm going to leave it on the outside of your pocket if that's okay. And then it should kick back in, hopefully any moment. But it's definitely unmuted. Okay.
And this one is work. Oh, that's better. Oh, yes, that's much better. You always have control when you have volume. I always think. Anyway, I did plant sciences, and I've always had a love for plant sciences. Somehow I feel, you know, when you get exposed to things when you're young, you just sort of feel more comfortable with them 40 years later. Anyway, it's a pleasure to come back. Now, I'm giving a talk which is not about my own research or speciality. I still run a lab. I have 4 or 5 students and a couple of postdocs. I'm going to talk about really the history of science, but in a particular context. So I hope that's okay. And it will be a little strange at times, so just so you realize that. My title is Science as Revolution. Now, when we think of revolutions, we usually think of major transformations in the spheres of politics, economics, social organization, religion maybe. For example, the Russian Revolution. And I have dear old Lenin up here with a couple of scientific instruments to make my point. But I think to these types of revolutions, we should add science, and it's not normally done so. Science both cultural through improved knowledge of the natural world and ourselves, and also through the impact that that improved knowledge can have on the development of human civilization. And I'm going to touch upon those things. In this lecture, I'll argue that science, a case can be made for it being the most long-lasting revolutionary activity known to humankind. And I think we need to think about that and maybe project it with our society, with our political leadership. And the reason I say that is because science generates systematic, reliable knowledge that stands the test of time. And as a result, can have long-standing consequence for society. It acts as a major driver for culture and civilization, and it changes the ways in which we live. And I want to illustrate some of these revolutionary advances by tracing the development of science from its first glimmerings in prehistory, and I'm basically making that up, okay, but, you know, because it is prehistory, through to today. And I'm going to argue that these revolutions have brought great benefit to humanity, and if properly nurtured and used well, will continue to bring great benefits in the future. So let me start really with probably what is a little bit of philosophy. Why is science such a reliable way of generating systematic knowledge of the natural world and ourselves? And simply answered, it is because of the way that we do science. It's based on a range of attributes, ways of working. These are not necessarily unique to science, but they are combined together in science in a very effective and powerful way. Science is based on reliable and reproducible observations. That's the first point. It generating accurate descriptions of the natural world. And it is it's this evidence which forms the bedrock of science, and that's one very distinguishing feature. The impetus to make observations and to carry out experiments often drives from curiosity. Curiosity is natural in children and often persists in a high level later in the lives of many scientists. I suppose that says scientists are often rather childish, actually, all their lives, which is also true, by the way, for anybody who's had any leadership role in that category. It is from the study of observations and experiments that regularities and patterns can be recognized. These in turn lead to ideas, to hypotheses, which can explain the workings of the world. And firstly, that requires an attitude of mind that the natural world is in principle explicable, in principle understandable. It's not the consequence of capricious supernatural forces. Something else that we need to remember, or at least Mr. Trump needs to remember. Explanations in science have predictive power. In physics particularly, the use of mathematics has been key in generating great precision in some of these predictions, and mathematics has influence in other areas of science too. Scientific explanations are often, not always, but often reductionist, looking for understanding of natural phenomena at lower levels of organization. Although, and this is important to recognize, this always has to be in the context of the behavior of the whole system. I'll say a little bit about that a little later. Imagination and intuition are important in generating ideas and hypotheses, and these can be tested with more observations and experiments. Now, this way of working has been well described by the philosopher of science, Karl Popper. This is a picture of Karl Popper, who emphasized the importance of trial and error in science. And I want to just explain this. He argued that a scientist considers the data obtained by observations and experiments, which are relevant to a natural phenomenon of interest, and then through leaps of imagination and intuition, develops a framework to consider that data. Then generates hypotheses or hypotheses to explain the phenomenon. These are then tested by using that hypothesis to make new predictions, which are then examined by further experiments and further observations. And if the data do not support that idea, that hypothesis, it should either be rejected or modified, and the new hypothesis tested further by new experiments and new observations. And what this means is, and it's important for us to realize this, is that science often proceeds by trial and error, with unsatisfactory hypotheses and ideas being rejected through a process of what Popper called falsification, the ability to falsify an idea. He went on to argue further that it is in fact this feature of falsifiability, the ability to falsify, that is a principal way of distinguishing science from non-science. Non-science is not so easily falsified as science. I mean, it's more based on assertions and the like. Now, a really important implication of how this view of how science works is that scientific knowledge will evolve. It will evolve, it will change, and is often tentative, especially at the beginning of an investigation, a beginning research. It is only after repeated testing that it becomes more secure. And this is something that often scientists don't fully appreciate, let alone our society. Now, science is also influenced by the way that scientists behave and interact with each other within a community. There's attributes linked with good scientists. Scientists should be open, honest, rigorous in their thinking, skeptical, especially of their own ideas. If anybody ever says they're a skeptic, ask them to be skeptical about their own ideas. Always fails, always fails. An effective science community should be interactive, should be collaborative. It should encourage the constant challenge of data, ideas and hypotheses, although always in a courteous way, in my view. It's the overall strength of the evidence and argument that matter in science, not the hierarchical authority of the scientists involved. I hope this rings a few bells with most of you in the audience, at least some of the time. The combination of these attributes, ways of working, produce a methodology that underpins science and is very effective at generating reliable knowledge. So when did such thinking begin? When were the first reliable and reproducible observations made that allowed recognition of regularities and patterns and explanations? Now, I think it's possible to detect such scientific processes in prehistory, and the examples I want to mention are the revolutionary changes which led to agriculture. I thought that would be appropriate for Rothamsted. Agriculture, metallurgy, and in the construction of astronomically oriented ritualistic structures, such as Stonehenge. And I'm now going to go into fantasy land and imagine perhaps the impulses that gave rise to some of the thinking around those three revolutions. Since there's no record of them, I have quite a free range to imagine. So the agricultural revolution was dependent, and here I'm talking to many more expert than me, was dependent upon the domestication of wild plants, the selection and cultivation of crop plants with desirable characteristics. First came about around 10,000 years ago in the Fertile Crescent of the Middle East, with the cultivation of cereals particularly, wheat and barley. Later, in other parts of the world, New World, with maize, and of course with rice. It requires continuous cultivation, experimental trait selection to generate cereals with large grains, low seed dormancy, convenient to harvest. And you see this nicely, for example, with the development of the maize crop. I imagine that some observant hunter-gatherer, because remember this emerged from a hunter-gatherer society, must have noticed unusual rare plants with desirable characteristics growing amongst a mass of normal plants. Perhaps what that hunter-gatherer observed might have been something like I observed this spring. Do you see this white bluebell embedded in a mass of bluebells in a Chiltern wood? And once spotted some, of course in this case a mutant form, then selecting that, collecting it, would lead naturally to the generation of potential crop plants. Now, the curiosity of such proto-scientists, I'm going to call them, their recognition of the potential usefulness of perhaps these unusual plants could have led to collection of their seeds, the subsequent propagation of derived plants. And over hundreds, even thousands of years, subsequent proto-scientists would go on to select even better combinations of characteristics. Eventually we would have the agricultural revolution. This occurred not once, but as I've already indicated, several times throughout the world with different crops in quite isolated places. It's difficult to imagine this happening unless there were creative and innovative individuals employing what we would now recognize as scientific approaches, careful observation, recognizing regularities and patterns. Given that it occurred in a number of different regions, it must be rather natural for us as a species and our distant Homo sapiens forebears to think and to act like this. Now, although later than the agricultural revolution, similar impulses must have generated the advances in metallurgy 5,000 to 8,000 years ago. A society that was dependent on stone or bone and wood for its materials, as we see here on the left, was in desperate need for metal, for tools and implements that could be used to cut trees, to harvest plants, inevitably for weapons. Now, to produce metallic instruments like this requires smelting metal ore at high temperatures. Once again, I try to imagine what might have happened and observe an individual who perhaps noticed that heating a copper ore produced a material that could be usefully fashioned to make tools. Perhaps it was burning charcoal produced from the campfire of the previous day on ground containing copper ore, accidentally generating the temperature needed to produce copper. Once done, it was noticed, it was successfully repeated. 2,000 years later, someone else must have smelted copper ore contaminated with tin to generate bronze, starting yet another revolutionary change in technology. Once again, difficult to imagine without thinking of individuals concerned with careful observation and observing regularities. However, these advances were not always utilitarian in character. Our prehistory proto-scientists were also observing and studying the heavens above them, particularly the movement of the sun and the stars as the seasons changed. The regularities they observed were incorporated in these great ritual structures aligned to important celestial events such as the longest day. The alignment of the heel stone with the stone circle of Stonehenge illustrated there, which corresponds to the summer solstice, is of course one the best of many, many such examples. And even more extraordinary than Stonehenge, I always find, is the tunnel above the entrance to Newgrange Barrow in Ireland, shown here, through which the light from the sun penetrates the depths of the tomb through that sort of box you can see just over there. See this here? And it only goes through there around the winter solstice. Tremendously precise alignment, you know, building in stone, and of course with religious overtones, but not obviously utilitarian. And this could have only be built on fantastically good knowledge of reliable observation of how the heavens were moving over the different seasons. Now, I've imagined all of that, of course, or imagined at least the thinking about it, but science becomes more clearly articulated in writings from classical Greece. The Ionian period started in Miletus in Asia Minor, that's on the east coast of Turkey, around 600 BC, so about 2,500 years later than Newgrange, produced Thales, Thales who provided ideas about the origins of the world. They were crazy ideas. He thought everything was derived from water, and the world was dynamic and in constant flow, but they were ideas trying to explain very abstract phenomena. So this is Miletus. It's true that it's Roman Miletus, and so 300 or 400 years later, and here is an imagined picture of Thales. Now, critically, and this is something perhaps not emphasized sufficiently, these early Greek scientists generated explanations which did not involve interventions from the gods. They did not invoke divine creators, as was the case for early Sumerian, Egyptian, and Babylonian creationist myths. Instead, they would propose that the planets were globes of fire in the heavens, rather than gods wandering around in the sky. Of course, they're not globes of fire, but at least it was rational. The important point is not whether they were right or wrong, but they were looking for explanations that were rational and did not derive from the supernatural. They were assuming, and I made this point a few minutes ago, that the world is explicable and can be understood by the rational workings of the human mind. And that is a revolutionary step. Difficult for us to quite imagine it now, but it is indeed revolutionary. Has to be said, though, not all in ancient Greece were happy with this rational approach. Socrates is reported to have been condemned by the political leadership in Athens to commit suicide by drinking hemlock, for corrupting the Athenian youth with his denial of the existence of the gods. And here we see Socrates from a David painting in the Metropolitan Museum of Art. He obviously likes talking. You'll see he's just about to take the hemlock and he's still lecturing everybody. Apparently, Plato is slinking off over there because he's so depressed that Socrates is about to commit suicide. Two features of science were developed by the ancient Greeks. One was the systematic description of nature, as described by the encyclopedist Aristotle, and the other was carrying out of experiments, which were first described, as far as I can find out, by Strato the physicist. The consequence was an explosion of ideas and scientific understanding, some of which, frankly, remains important today. Aristotle provided the descriptive basis of biology, and together with his followers founded the philosophical school called the Lyceum in Athens, which really was the first scientific research institution. I mean, they talked rather a lot, but they were making observations and so on as well. Democritus proposed a theoretical atomistic model for matter, anticipating atomic theories of Dalton 2,000 years later. Aristarchus argued for a sun-centered heliocentric planetary system, not accepted also till later. Eratosthenes not only concluded the Earth was spherical, but also by observing the lengths of shadows at noon, determined in Alexandria and Syene, actually determined with completely extraordinary precision the diameter of the Earth, within 10%. You know, we're talking over 2,000 years ago. I mean, extraordinary. Archimedes founded the science of mechanics until his work was tragically terminated by a Roman soldier at the siege of Syracuse. On the whole, the Romans do less well than the Greeks in the history of science, it has to be said. Syracuse was besieged by the Romans, and when they took the town, poor old Archimedes was killed. The Greeks brought about a revolution in ideas that changed our world forever. They introduced the concept that the world was comprehensible. They liberated humanity from the yoke of mysticism and superstition, mostly. They brought about long-lasting changes in our knowledge. They started the development of mechanical technologies and of medicine for the benefit of humankind. It was a revolution that began the long journey to the Enlightenment, an enlightenment which I hope still continues today. Realizing that the workings of the natural world can be understood meant that careful observation and meticulous experiment could be gathered together to provide knowledge and insight, and how that knowledge could be applied in useful ways to help society. So I'm going to fast forward to England at the turn of the 17th century. Francis Bacon, courtier, statesman and philosopher, who was laying out his approach to science. Here he is, Francis Bacon, about 1620. He emphasized the need for the gathering of reliable information and the taking account of this information, these particulars, to then formulate generalities, noting when occurrences of specific particulars were correlated with specific outcomes, and when they were not. He was looking for correlations. He famously argued for a skeptical approach in the pursuit of knowledge, saying, this is one of my most favorite quotes, this is straight from Bacon, if a man, by the way, there were obviously no women in the early 17th century, but we just have to live with that. If a man will begin with certainties, he shall end in doubts. But if he will be content to begin with doubts, he shall end in certainties. Great. Really great. He advocated that knowledge is power, and that establishing a legitimate command over nature leads to the relief of man's estate. In other words, that science is useful, very relevant, of course, to Rothamsted. However, it would have perhaps been best if he'd confined himself to thinking about science rather than doing science. Driving during winter in Highgate in London, he stopped his carriage just off Hampstead Heath, bought a hen and stuffed it with snow to see if it would delay putrefaction of the bird. As a consequence of his outdoor experiment, he caught a chill, developed bronchitis, and died several days later. Obviously, it's safer thinking rather than doing experiments. Meanwhile, at the same time, but in the warmer climes of Italy, Galileo was more successful with his experiments and observations. His work studying the motions of balls descending inclined planes established mechanics as science and importantly connected physics with mathematics. He stated that the book of nature is written in mathematical characters. But it was his acute practical observations combined also with his rationalism which led to the revolution that provided the final evidence that moved the Earth from being the center of the universe to a planet circling the sun. Thus began a process whereby our terrestrial globe has become increasingly insignificant, to just frankly a speck in the universe. Our sun is a star, just one of billions in our galaxy. Our galaxy is just one amongst the billions that make up the universe, and there may even be countless universes. And this revolution started here, when Galileo turned his simple telescope towards the planet Jupiter and discovered what he called the Medici Stars. He was cozying up to potential funders. I'm sure none of you in this room ever do that sort of thing. And of course, the Medicis were potential funders. So he described stars circling the planet, and he named them after his former pupil and subsequent employer, the Duke of Tuscany. Clearly, not all celestial objects were orbiting the Earth. This led strong observational support to the heliocentric views of Copernicus, which can be traced back to 1500 years previously. Eventually, this led to his conflict with the Catholic Church, although it should be said the Protestant Church were equally avidly against his views. Both were concerned that the Copernican system could have worse consequences. For the Catholics, worse consequences than both Luther and Calvin together. So Galileo was forced to recant his ideas, possibly after encouragement by being shown the instruments of torture. So, this was about the least ghastly picture I could find on the website of torture. Most of them just turn my stomach over, you know. This one I could live with. Science does not always sit comfortably with religion, nor sometimes with politics and ideologies that do not respect the importance of evidence and rational argument. This marked perhaps the first stirrings of the Enlightenment that Immanuel Kant would eventually describe as the emergence of man from his self-imposed infancy, by which he meant that humankind gained the resolve and the courage to use reason to understand the world, following the Roman poet Horace' dare to know. And this sentiment, the reason I mention it really, was central to the founding of the Royal Society in 1660, which ushered in the age of modern science. Its motto, nullius in verba, roughly translated as take no one's word for it, which reflects the emphasis on the need to rely on demonstrated observation experiment rather than established authority. And this is the Royal Society's coat of arms. You'll see nullius in verba reflecting exactly that. The early pinnacle of success, of course, for modern science was based on the application of mathematics to physics. It was the work of Isaac Newton, who's shown there on the right, deeply unpleasant person, by the way, whose laws of motions led to the idea of universal gravitation. It provided a quantitative description of the motions of visible bodies, demonstrated that the motion of a small terrestrial object, such as an apple falling from a tree, was subject to the same laws that apply to the motion of large celestial objects like planets orbiting the sun. There's a fantastic intellectual span there, just to sort of recognise that. The apple falling off the tree could be related to the same laws that could explain planetary motion. I mean, now we accept it, but pretty special. Important to remember, Newton's laws did not provide a mechanism for gravity. The universality and scope of the law of gravitation and the predictive power led to great precision in the calculations as to what would happen. But he had strange, almost metaphysical concepts of action at a distance and didn't have an actual explanation. Again, that isn't always fully recognised. But it did consolidate what I'm arguing is a revolutionary view that the world can be understood by the use of reason and experiment. It also leads to important applications. Robert Hooke, who also contributed, by the way, to ideas about gravitation, but was expunged from history by the priority-seeking Newton, who even burnt his portraits, apparently. I mean, just in case you think scientists only behave badly now, I think we've been behaving badly for centuries. What did Hooke say? He said, scientific discoveries concerning motion, light, gravity, magnetism, and the heavens, all things that you were interested in if you were a 17th century scientist, helped to improve shipping, watches, optics, engines for trade and carriage, all things that were of interest for application to humankind also in the 17th century. But once again, science is revolutionary in character. It changes our view of the world, it changes what we can do in the world. Knowledge of the movements of celestial bodies was central to navigation. Without it, you could not carry out journeys across the globe. It's another revolutionary step in the history of humankind that has a scientific basis. Stephen Shapin, he's an historian and sociologist of science at Harvard, has emphasized another aspect of why the Royal Society was so important for the birth of science, because it generated a way of working which led to a scientific culture or a scientific sociology. Again, we don't often think about that. Science was open, in principle at least, to all professions, to those of different religions, to those of different races and classes. Not to women, I have to repeat yet again, for another 300 years, but was much more open than most bodies of the time. It was inclusive and tolerant and international and provided a community promoting discussion, criticism and advice. It invented the scientific journal, Philosophical Transactions, incorporating the concept of criticism and peer review. The Society emphasized the importance of the public demonstration of experiments, the need to provide sufficient information for that work to be replicated elsewhere. These are all sociological practices which are pretty much embedded in the way we do science today, and they were nearly all put in place between 1660 and about 1690, and in the Royal Society of London. Robert Boyle, another founding fellow of that society, argued that experiments should be reliable and reproducible and witnessed. He recommended public performance. The pursuit of scientific endeavour, in other words, embraces communication of those advances and therefore encourages debate. And what emerges from this is another idea, the importance of consensus opinion amongst the scientific community. And sometimes consensus is used as a dirty word when people want to try and undermine certain scientific arguments. But if an idea or a set of experiments and thinking are found to be convincing by the majority of scientists who are familiar and expert in that area, then these ideas gain extra weight by having passed that scrutiny, often intense scrutiny. And this is why the consensus opinion of experts in an area is important, as it probably will give the most reliable overview available at the time. Not always right, but most likely to be right. And it is not the case that consensus is a lazy agreement. It's quite the opposite, in fact. The consensus will have been arrived at because it has stood the attacks and commentaries of other experts. And that's how the scientific consensus works today. If an idea our hypothesis has value, it generally spreads rather rapidly through the scientific community and becomes the new consensus view. If it has limited or no value, it will not do so. Despite all the attempts of lobbyists to promote fallacious views in the lay public arena, as can sometimes happen in some scientific areas important for public policy, and climate science has suffered from these sorts of problems, from criticism from people who simply have no idea how science is really done. So the Enlightenment and the Royal Society, together with other scientific academies of the 17th century, started modern science, and the consequence of this was knowledge that formed the technological basis for the Industrial Revolution of the subsequent 2 centuries, and which continues today. And that, frankly, cannot be overestimated. It literally underpins the making of the modern world. The advances were legion. The development of new energy sources with steam, electric and internal combustion engines, later nuclear and novel renewable sources of power, use of new materials, iron, steels, ceramics, plastics, the invention of increasingly efficient machines of manufacture, the power loom, the spinning jenny, leading to the modern robotized factory of today, new means of transport, the locomotive, yes, that's up there, the steamship, the automobile, the airplane, the spaceship, advances in communication and the management of information, the telegraph, the radio, the television, the computer, the World Wide Web, all of this stuff. But unfortunately, of course, together with these advances for the good of humankind, there have been the construction of increasingly more effective and deadly weapons of war. It's difficult, frankly, to imagine any aspect of our present lives which has not been influenced by the developments of science. They have brought revolutionary changes to everyone on the globe. The Industrial Revolution was mostly based on the physical sciences, and we tend to underestimate the contributions from the life sciences. For some reason, the history and philosophy of science is written by those interested in physics more than biology. I've never fully understood that. I think it was because when you were at school, you know, if you were interested in science and weren't very good at maths but could draw, you did biology, you know, whereas you know clever ones did physics. You know, my daughter's a physicist, and I'm not bitter. For example, again relevant here, so I thought I'd mention it, scientific approaches have gradually increased agricultural production, and this is the classic Rothamsted experiment, such that crop yields today for each acre of land under cultivation are many times higher than in the early 18th century. If proper economic, social and distribution conditions were in place, our improved scientific knowledge means that no one should be hungry on the planet, and a situation that was frankly inconceivable in former times. The life sciences have also brought about further new ideas and concepts which have led to revolutionary changes and challenges to opinion and orthodoxy, no more so than, of course, in the idea of evolution. Charles Darwin illustrated here his painstaking observations, meticulous arguments made the case for evolution. He argued that living organisms have evolved and are related by descent. He also postulated a major mechanism for evolution, that of natural selection. This demonstrated that the life sciences could also be understood in terms of universal laws, just like physics. And as Darwin himself recognized with his famous last sentence in The Origin of Species, where he refers back to Newton, he said, this is Darwin, "Whilst this planet has gone cycling on according to the fixed laws of gravity, form so simple a beginning, endless forms, from so simple a beginning, endless forms, most beautiful and most wonderful, have been and are being evolved." He was relating his ideas to Newton's laws of physics. But most importantly, and obviously still contentious for some today, Darwin's ideas moved human beings from being specially created to being related to the rest of the living world. Just as Copernicus had moved the Earth from being the center of the universe, so Darwin moved humankind from a unique position separate from the rest of life. That's why these two ideas are so important to our cultural history. Should be recognised that Charles was not the first to propose evolution. His own grandfather, Erasmus, was a proponent of evolution in the 18th century. If you know his book, The Love of Plants, for example, you'll see some accounts of his ideas about evolution. But Charles was the first to assemble the wealth of observation and experiment and critical, closely argued reasoning, which was necessary to convince his colleagues and subsequently the world of the validity of evolution. Science advances by good ideas, but it is completely dependent upon reliable and reproducible observation and good rational thinking, and it's that which gives science its strength. Another great advance of the 19th century with revolutionary consequences was forged by John Dalton, non-conformist teacher in Manchester of rather humble origins. Quite interesting actually how quite a number of these ideas emerged not from the great centres of learning actually. I might comment a bit more about that. What Dalton did by a study of gases and the relative weights of the elements, gathered experimental evidence in favour of the existence of particulate atoms, increasing in mass by unitary increments. He proposed that atoms combine together in simple ratios to generate molecules, and gave the first empirical support for, as I've already mentioned, the 2,000-year-old atomic speculations of non-divisible units proposed by Democritus as the ultimate structure of matter. His work illustrated another aspect of science, the strength of explaining a natural phenomenon in terms of the behaviour of components acting at simpler levels. Many scientific explanations are expressed in what some call reductionist terms, and some compare reductionism in an antagonistic way with holism, which emphasises the whole behaviour of the system responsible for the phenomenon under study. In my view, this antagonism is misplaced, however, because reductionist explanations are powerful, but to be powerful, they always have to be placed in a holistic context. I think it's one of these really artificial divergences. We are both holist and reductionist at the same time. They are not incompatible, they are mutually reinforcing. Dalton's achievements, together with others, such as the great chemist Lavoisier, who's shown here, also by David, laid the foundations of chemistry and of the chemical industry, again with great revolutionary consequences. Talking of revolutionary consequences, Lavoisier lost his head to the guillotine about 10 years after this portrait was painted. And David was on the committee that condemned him to death, the man who did this painting. Tragic, really. And Mrs. Lavoisier was his research assistant who worked with him in the laboratory. Something, one of the very first female practicing scientists. So, a second great scientific advance of the 19th century was built on the power of on reductionism, and of course came from plant breeding experiments of the Czech monk Grigor Mendel. Now his experiments led to a particular explanation of heredity, not atoms. That is, that inheritance is based on non-divisible units, which we now call genes. And this spawned discovery after discovery, eventually. I mean, particularly in the 20th century, genes were found to be made of DNA. The double helical structure gave rise to the idea that DNA is a digital information storage device, which is what it essentially is. That led to the edifice of molecular biology, built on genetics and biochemistry. Louis Pasteur laid the foundations of the biochemical mechanistic explanation of life with his studies of sugar beet fermentation by yeast, from which he concluded that chemical transformations are the physiological characteristic of life. Pasteur's work undermined, this is Pasteur, the concept of vitalism, by proposing that living organisms can be understood in terms of physics and of chemistry. And these have revolutionary influences of this advance, leading to human health and increases in longevity of humankind. Modern medicine is built, and the pharmaceutical industry, on this sort of thinking. Only 100 years ago, it's good to remember this, even in developed countries such as the UK, life expectancy was around 50 years. Probably only an increase of 15 years around the agricultural revolution 10,000 years previously. In the last 100 years, it's increased to 80 years, and much of that is to do with science. Why don't we shout that from the rooftops? Much of that. So these changes have brought revolutionary changes, both for the well-being of individual human beings, and as a consequence, the whole demographic structure of society as well. Once again, revolutionary. Another revolutionary consequence, more abstract for society, is what does science tell us about questions like, what does it mean to be human? If, like other living organisms, human beings are to be understood in terms of their inherited genes and their chemistry and their interactions with the environment, what does this mean for our sense of what we are, for free will, for the use of punishment and justice, for equality, for racial, gender, or other differences? There's lots of implications here. The profound questions, studies based on evolutionary genetics, animal behavior, have implications for ethics and morality. Science has an annoying habit of invading other domains of human activity, which at first sight it doesn't seem to have much impact. This was the case for Galileo and in Darwin. It's still the case for today. It invades domains once thought to be solely of philosophy, of politics, or of religion. One other thing, and you'll be pleased to hear I've nearly finished, by the way. Are you getting tired, or is it all okay? Just big deep breath, it's soon over, okay? Big deep breath. Modern physics has had another impact, and it may have an impact for biology too, which is also revolutionary, and we could say it's on the nature of human knowledge. Have I lost the mic? I'll keep, oh yeah, I've got it back, jolly good. Einstein, in his theory of relativity, proposed a continuum of space-time, which did give a mechanism for gravity, by the way. That did give a mechanism. And that undermines the common sense view of the world expressed in terms of time and the three dimensions of space. It's different. Apart from brilliant reasoning, Einstein's approach meant that the drive of science to predict and explain natural phenomena resulted in a theory that no longer is quite in accord with our common sense. That is, this Kantian view of three dimensions of space and time. And then 20 years later, after Einstein, studies of atomic structure led to quantum mechanics, which is an Alice in Wonderland world, a place where Schrodinger's cats can be alive and dead at the same time. But despite not being explicable in terms of a common sense understanding of the natural world, this produced the subsequent standard model of physics, which is what my physics daughter works on, by the way, and has led to extraordinary precision in the predictability of behaviours of the ultimate constituents of matter. If you go into a bookshop and you look at the popular science, you could be forgiven for thinking that the only areas of interest are evolution by natural selection and string theory. But putting that aside, if you open a book which describes relativity, you sort of understand it. Yes, you read it, you read all the metaphors, you sort of understand it. You're sitting on a steam engine going fast and listening to whistles and all that sort of stuff. Have you read this sort of thing? You then close the book and somehow it all slips away. And it's slipping away because it's no longer part of the common sense world. And if you now turn to high energy physics and atomic theory, I mean, you are in deep trouble. It's utterly incomprehensible. But the reason I'm mentioning it is it's a revolutionary shift of human knowledge where explanations work beautifully, but they're not in our normal common sense understanding. And where physics leads, I think sometimes biology follows. And I sometimes wonder whether the complexity of living organisms and the way they work will also lead to strange and non-intuitive explanations. I don't really know what I'm talking about, but I sense there's something there that might lead to a lack of the common sense world. It should, of course, be said that these physical studies led to the nuclear bomb which has also had a revolutionary impact on society, certainly for most of the second half of the 20th century, dominated by the Cold War. I've argued that science is truly revolutionary, more so than the revolutions based on politics or ideology, or even in the long term, religion. What can we learn from the past that will help us in the future to ensure that revolutions in scientific knowledge continue to improve the human condition? Now, this is where I want to end my talk. The first of these questions is, how do we do good science? And I'm not going to spend any time on that. Great scientific advances are driven by excellent scientists given good resources. And if we get that right, it will work. So I'm not going to say anything more than that. I'm probably treating to the converted there, but I think that's important. However, more difficult is the second question, ensuring that science brings about improvements in the human condition, which of course is part of what you're trying to achieve here in Rothamsted. This requires good and healthy relationships between science and society. We need to ensure science is used for public good. Over the millennia, science has generated knowledge that's been used for other purposes, for war and oppression, for example. Bronze, as I've mentioned, led to both useful tools but also to weapons, steam power to railways and to dreadnoughts, atomic physics to nuclear energy and the nuclear bomb. Ultimately, making good decisions about the use of knowledge based on science depends on societies with the right values underpinned by healthy and effective democracies. For science to play its proper role requires a public at ease with science and a democracy that can cope with the complex decisions involving science. But there are threats to this. We need to be aware of those who mix up science based on evidence and rationality with politics and ideology, where opinion, rhetoric and tradition can hold more sway. We need to be aware of political or ideological lobbyists who do not respect science, who cherry-pick data or arguments and do this to support their predetermined positions. We need to be aware of those who distort science to support particular fundamentalist beliefs, not based on the rigor of rational argument and data, but on faith or revelation. We need to be aware of the relativists who argue that knowledge is culturally determined such that all views are acceptable, even those not supported by reliable evidence and rational reasoning. Revolutions are unsettling and are strenuously often opposed. This was the case with Copernicus, it was the case with Darwin. No doubt there were some who rejected the agricultural revolution of Neolithic times, just like there are some today who reject the potential advantages of GM, not based on rationalism or any other good arguments, even when they can be used for the public good. At its best, society shows it can deal with these threats. I'm optimistic that in the future society will increasingly see the value of science in bringing about revolutionary changes to our knowledge and also revolutionary improvements in society and the human condition. And that's why I'm arguing science is truly the most long-lasting revolutionary activity known to humankind, and properly organised will continue to bring great benefits to us all. And thank you very much.
We have a good amount of time for some questions, but please wait until the microphone comes to you, so that we can record it. So, up there. Got one down here, John.
John. I'm a bit deaf, so do shout or wait for the microphone.
You've got the right guy.
Yeah, I know.
Wonderful, Paul. If you invoke the idea of proto-scientists contributing to evolutionary developments, like you did with wheat, then we'd have to think about the creation of Homo sapiens, particularly the sapiens bit. This is obviously an area of great danger. Possibly it could lead, if it proves to be the case, to dangerous thoughts. But on the other hand, we couldn't really test it because, of course, by proto-scientists involving themselves in plant breeding and possibly human genetics, then they would condense the actual number of generations necessary to move from, say, Homo erectus to Homo sapiens. Do you have any thoughts along this likelihood, or how you deal with the outcomes?
I'm not sure I've got anything terribly useful to say, to be honest, John. I mean, I think it is quite interesting to think how Homo sapiens came about. It's not the question you asked, but I mean, I don't know if you ever went to that exhibition in the British Museum called Ice Age Art, for example. That was amazing, and you see signs of creativity and so on back 40, 50,000 years ago. It's probable that it can be pushed back to 100,000 years, and what brought about that change, I think, is really striking. What you're referring to, I think, mostly now is in the future we have the ability to control our genetic destiny with manipulation and so on of the genomes. I think this has to be done with enormous care, in part because we simply don't understand what we're doing yet, and there is an arrogance in thinking we do. We have knowledge, but not the knowledge yet to be able to engineer, I would say. And even before we can consider that, we need to have all the proper discussions with society. So I would say let's be really careful. I sort of ducked your question, really.
I very much like your comparison of science to evolution. However, it's also said that revolutions tend to consume the children. So if we were the children of science, or people who do science, how would you ensure that we actually attract the best people and retain the best people in doing science?
Well, we have to encourage people to do, I'm not sure if I quite got the idea of how do we promote science, or how do we sort of best engineer science for people, for the public good. I do think we have to have conditions where science can prosper and where scientists can do their work. I think that has to be understood in the context of the fact that scientific research ranges from discovery work of the sort I do, which is just understanding the world, through thinking about translation of knowledge into something more useful, through to direct application. And what distresses me is how people in different parts of that spectrum fight other people in the spectrum. That is just crazy. We are all needed in that spectrum, and we all do need to interact one with another. Different areas interacting upstream and downstream affect each other. And I mean, that is just part of what science has always been. And I simply don't understand it when people argue against that. I do happen to think that in most parts of that spectrum, scientists to work effectively do need a freedom to pursue their ideas, that the closer you are to application, the more top-down it's likely to be, because you have to have particular objectives. And if you have too much restraint or too much forcing in certain directions top-down by committees of ancient people with white hair, I think you're likely not to get very effective scientific advances, is my view about all of that. But to deal more with the second question, all of this has got to take place in the context of the public and society being comfortable with science, which requires a proper engagement, proper communication, a humility in what we know and what we don't know, and we need to project that sort of relationship. And so it's a complicated thing. The UK does it pretty well, can I say, having lived and worked in a number of countries. The UK is pretty good at this. And one of the most distressing things for me about the Brexit is that we had quite an important role within the EU in guiding or helping guide with other good scientific nations. And we could have a bigger impact as a consequence. And we're clearly reducing our impact dramatically by floating off into the Northwest Atlantic.
Thank you very much. That was excellent talk. I'm interested in you saying, and I agree with you, that science advances by good ideas. And I just wanted to ask a personal question. When have you had your best ideas, and where do you think they have derived from?
I think I've not had very many really good ideas, to be quite honest. I've had many ideas, and I always talk to my colleagues who work with me, you know, the ideas are cheap. really cheap, and nearly every idea you've had, somebody else has had before you. I mean, and people don't realise, you know, often young scientists think every idea is they're the first to have had it, and usually that isn't the case. So, you know, the idea of evolution was one which existed hundreds of years before Charles Darwin. You need to support the idea with good observation, good experiments, good ways of actually getting at it. I found that personally, working in the life sciences, several of my better ideas have been a consequence of being led by nature itself. In other words, although I argued Karl Popper's position of hypothesis generation and testing of hypothesis, which I think is very powerful, that sometimes just observing nature and using nature therefore to formulate ideas almost for you is very, very important. So I work with yeast, I work on the cell cycle and other things to do with yeast, and just seeing different mutant forms which I had never imagined has generated certain ideas. So that would be one observation to make there. The second one is that just sometimes having really bold ideas, it do work. And when I postulated that the genes that controlled the cell cycle in yeast might be conserved in every living thing, I mean, in the early 80s, that was not thought likely. And so it was an interesting idea, but of no value. And then I thought, well, we can just take a human library, cDNA library, the first ever made actually, and not by me, by Paul Berg, dumped it on yeast cells that couldn't divide because of a defect in their main controlling gene, and use yeast to find out whether the human gene was there. Now that was a ridiculous experiment that had no right to work, but did work, and showed that that humans had exactly the same gene that would do the same job, functionally equivalent, not just structurally similar. And that was a combination of idea and experiment to generate. So those are my two sort of good ideas.
Not revolutionary, but
there's several here, so let's keep going.
Thank you very much. You made a big point about the public being comfortable with science, and you've alluded to various threats to that, whether it's the sort of Trump, Nigel Lawson type, or people just not being interested but having to use the product of it, or people getting sort of simple issue, slightly nutty ideas. What's your advice about how to deal with that, to make a better situation?
Well, the first thing is with political leaders, I think the thing to do there is to make friends with the political leadership, okay? Because most of them will listen. I mean, you have crazies like Lawson, of course, who you mentioned, who's just stuck in his own ignorance. But most will listen if you spend time with them and explaining things, which is something I had to do at the Royal Society, of course. What doesn't work is simply to go and talk to them when you want to complain and whine, which I have to tell you is what 95% of scientists do. They only go and talk to them when they're complaining. I mean, do you like people who just talk to you when they complain? Of course you don't. I mean, if they just come into your office like they probably do when they want to complain about something, I mean, you just want to see the back of them as soon as possible. So you have to make friends with the political leadership. Not all of them will be great, but most of them will be and react to that. So that's one thing. With the more general public, I think we have to support those of our colleagues who are great communicators. Now, I mean, there are some who are great communicators, and I do mean great communicators. I mean, somebody like me is sort of okay, but when I see a real professional, I realise I'm a complete amateur, and we shouldn't sneer at them when they make a small mistake on the telly. If you've ever sat and looked at a camera lens for 2 hours, repeating the same sentence because of whatever, and then until your brain is mashed up like spaghetti. I mean, if we've got great communicators, encourage them to do it and forgive them their small errors, and they will inspire, I think, the future. And the third thing, really, is that we have to project ourselves as being ordinary members of society with a certain amount of humility. We're not the magicians, we're not, you know, the shamans, and we have a certain knowledge which we present to you, and we'll discuss it further. I think these are the characteristics.
Do you think that to some extent we're the victims of our own success, being scientists? all the best evidence, because there's so much stuff out there, even if you try and scour literature, for example. But I think even more importantly, we continually show that things are more complicated than we thought. And in dealing with the public, that's quite a hard message to understand, because we're not to say that we can change things, but we're forever saying, oh, but you know, it's more complicated than we thought.
So I agree with both of those points. The second first, I mean, the world is complicated, the living world particularly so. And this is hindering biomedical advances, in my view, that we are trying to rush to translation before we've understood. We've become lost in translation in some respects. The advances in drug development and so on have not gone as fast as we would like to see, because we don't understand how we work properly, because we are horribly complicated. And you'll understand that again, it's horribly complicated producing sustainable increases in agricultural production. So we do need the humility of recognizing what we don't know whilst embracing what we do know. And it's a delicate balance to actually do that. In being, the first point you made is, it's indeed true. I mean, you think how much science has expanded in recent years, and knowledge has expanded. When the Nobel Prize was started in 1901, I think, somebody did a calculation, there were 3,000 scientists in the world. I don't know if that's true, but let's say it is true. I mean, there's 500 scientists at Rothamsted, okay? So it was only 6 times bigger than Rothamsted, if that's true. And the immensity of the expansion of scientific knowledge in recent years has been dramatic. And a consequence of that has been several ones that I think are disturbing. One is we get more and more focused on a smaller and smaller problem. And actually that doesn't help science, because you need to have not only depth of understanding, but a good peripheral vision as well. And the second thing that worries me even more in the life sciences is the teaching of our students learning the subject. I mean, all that happens is the